The cognitive properties effect on the liquid state is to increase. Wow, that was crazy. It's to increase range of the liquid state. So for all practical purposes, the temperature of freezing goes down and the temperature of boiling goes up. So it's a liquid over a larger range of temperatures. All right, so this is one particle. It will not break up because barium sulfate is insoluble. This breaks up into three particles. Both of these break up into two particles. So these guys are basically tied. This is most effective. And this is least effective. And it's not just like half as effective as this of the two, because there's no charges. This doesn't dissolve, so there are no ions. So it's even worse than being just one thing instead of two things or three things. It's not a charged particle. So it would, I mean, might minor assist in traction, but for the most part, it's not gonna, I mean, it won't change the freezing point of water. So effectively, the freezing point part is 0. Blow dryer. Okay, so two things. Water from tap is not pure. And you are salty. So those two things together make the tub the solution in the tub is an electrolyte. So of course it's going to cause electrons to flow. Okay, so nerves transfer electron or information with electrons. This is why when you put a STEM machine on your quadricep, the thing flexes. Doesn't matter where the stimulus comes from. If there are electrons there, then it's going to do what it's supposed to do. And in this case, for the muscle, it's supposed to contract. All right, so nerves transfer electrons. And in a fluid, so the electrons are going to need charges to move through a fluid. So one nerve cell goes to send electrons over to the other nerve cell, and I need something to move it over there. It needs a cation to move stuff over to the other side. So that's why you need electrolytes. Glucose is highly soluble. Would it alleviate those cramps? And the answer is it would not alleviate those cramps because glucose is covalent. No charge, no ions. So it wouldn't be able to transport electrons from one nerve cell to the other. All right, so I've got basically a unit calculation going on here. Freezing point for water, and we've got a pound of water, and I'm going to make a pound of calcium chloride, and we're going to put it into a gallon of water. Alrighty, so that is temperature freezing is the change in the temperature of the freezing point is equal to the N value times the Kf value times molarity. The N value of calcium chloride is 3 because it's CaCl2, so it busts up into 3 ions. And then the Kf value I gave you is 1.86 degrees C molarity. And that's an experimentally determined value. You can't calculate that. You have to, figure out what that is. So now we need a molarity. So I've got pounds and gallons. So I'll put 1 lb here, 1 lb, and then I'll put 1 gallon in the denominator. And so for every 2.2 lbs, that's 1 kilogram. And then for every 1 kilogram, that's 1,000 grams. And then let's see, what is the molar mass of this? Yeah. So I've got 40.078 plus 35.453 times 2. So 110.981. So 110.981 grams for every 1 mole. So grams are gone, kilograms are gone, pounds are gone. So I got my mole unit where I want. Now I need to get out of this gallons thing. So for every 1 gallon, there's 4 quarts. And then for every 1 quart, there's 0.948. No, turn it, we're gonna take that up just so I'm correct. So 1 quart in liters. That was right. Well, no, actually I wasn't. It was close. 6 liters. Okay, so the quarts are gone, the gallons are gone. I've got liters and I've got moles. So there's a molarity value. So let's see, 1,000 divided by the 2.2 divided by the 110 number divided by 4 divided by 0.946. So I got 1.08. And so if I plug in 1.08 molar here, the molarity cancels out. The only unit I have left is degrees C. So that number times 1.86 times 3, and I get a temperature change of 6. So my answer is -6 degrees Celsius. That's the freezing point of this substance. Okay, what else we got? Okay, so if I throw in NAs, this has got a full-fledged plus charge. This oxygen is going to be attracted to that sodium. This oxygen is going to be attracted to that sodium. This oxygen attracted, this oxygen attracted, this oxygen attracted, this oxygen attracted. What ends up happening is this water molecule here reorients itself. Here's my oxygen moving in towards the carbon or towards the nitrogen, sorry, the sodium, and you end up with a change of orientation of the water molecule. This guy turns, so it's like this now. This one turns, so it's like this now. This one turns, so it'll be in that orientation. So all of that's broken. This guy turns in this orientation, turns in this orientation, pointing their oxygens towards the sodium. What I've done is I've broken this connection, that connection, that connection, that one, that one, that one. And now that the crystal lattice structure is broken, I'm not in solid form. I am in liquid form. That same exact situation happens if I'm talking about the chlorine, but in backwards way. So my chlorine is here with a negative charge. That hydrogen is attracted. That hydrogen is attracted. That hydrogen is attracted. That one's attracted. That one's attracted. That one's attracted. All of those water molecules reorient themselves and they break that intermolecular force. This one, this one, this one, this one, this one. And now again, I no longer have a crystalline structure, so I no longer have a solid. So the fact that the water molecules are held together by partial positives and partial negatives from hydrogen bonding can be disrupted if I throw in a full-fledged plus charge or full-fledged minus charge. That changes the orientation of the water molecules, disrupting the crystal lattice structure and causing it to liquefy. All right, what do we got next? Is that it? Oh, that's the last one for this. Or is it? Yep, it is. Okay. All right. That's it for this homework.